Hey guys, hope you are doing well. Today is the first video in a series that I am doing on RAG, retrieval augmented generation. We're going to go through each of the different pieces of that puzzle, what they do, different ways you can set them up or do them, how it works, some tips and tricks on the general pipeline and things like that. We're going to do a couple different videos here with each of these pieces here that we need for RAG. The first one today we are going to start with is the embedding model. I have some code we're going to take a look at, some graphics we'll walk through, and then kind of take a little bit of a basic level of what RAG is, so we at least know what the goal of the conversation is, because we are just focusing on this small piece of it. So with that being said, let's dive into it. So what is SBERT? That's what we're going to start with. SBERT is a semantic similarity model. The entire goal of this model is to take different pieces of text and understand how semantically similar they are. These can be different lengths. You could have one be really large, one be really small. You can have them be the same, very long, very small. But the entire goal of this is semantic similarity. Now, it does do some other things for you, but really, in terms of what we're talking about with RAG, the main goal is semantic similarity. This is very different from some of the other sort of options that you have here for the embedding model. The reason I like SBERT specifically, there are a lot of options out there, such as the OpenAI ones, Gina, things like that. One, SBERT is very lightweight. You can deploy it in a relatively small environment. You don't have to pay per API call or anything like that, which allows you to have some control over the cost and the compute power with your embedding model. I also really like it because it is fine tunable. It's an open source library, so we can fine tune it. And as we will see as we kind of go through this, and there will be a separate video for how to fine tune SBERT, you'll see that that is incredibly valuable for RAG. Anyways, I am going to walk through here what is a RAG pipeline at a very high level, just so we are talking about the same thing and we understand kind of what we need to do here for this to make sense for SBERT. So we have our knowledge base here of documents. These are the documents that we want to search through. We want to be able to do sort of the question and answer style that RAG is very popular for. There are other use cases, but sort of the query and the answer is the most popular that we have here. A user query comes in. We check a vector database, which contains our documents, contains our information. And we find at this step where you see the top K chunks, we find the most similar document chunks to the user query. And we do that using semantic similarity. So we have all of these documents in this database. A user query comes in. We only care about the ones that are relevant to the user query so that we can, create the answer for the query. And so we just want to figure out how can we grab the ones that are most relevant. And this is where semantic similarity and SBERT specifically come into play. From there, of course, we pass all of this to the LLM and we generate a response. But today we are just focusing on this part here where we are understanding the semantic similarity part. So let's take a look at how you can use SBERT. SBERT is a short form for sentence transformers. Almost nobody calls it sentence transformers. SBERT is definitely the more popular name. We're going to install the library. I have installed it previously in my Google Colab, so it's just going to tell me that I am already good to go. We're going to install it. We are going to load The model, there are a couple different model options in SBERT, mostly focused on different sizes and things like that. This is by far the most standard one, the all mini LM L6. But like I said, there are other options, bigger, smaller, focused on different stuff. Really just depends on your use case and what you're trying to do. But this is by far the most standard one that we have here. So I'm going to load up the model. And the first thing we are going to do is we are going to encode some sentences. Now, what encoding means is we are going to transform these sentences into a number representation so that we can do a similarity between them. Computers do not, out of the box, understand characters and things like that. Of course, they are numbers focused, ones and zeros. Encoding is converting these strings of text into numbers so that we can do the comparison. Essentially, each of these sentences is going to turn into a long list of numbers, and how similar those long list of numbers is how similar the sentences are. That's due to the numbers in that list differing based on the words that are in that. And when we go through the fine-tuning process in the separate video, you'll see that kind of the goal of the fine-tuning is saying this sentence, this word, these are more similar, and you're teaching the model what similar means for your specific use case. Of course, the specific use case for these general models out of the box is really the entire English language and the corpus of text that we have. But you will see that through fine-tuning, we can change that around and make adjustments for what we need it to be for our specific, RAG pipeline or something like that. So here are the sentences. We are next going to embed them. Encode, embed, you'll hear me use both of those terms. Embeddings, as you can see here, they're a numerical version of what we have here. We can see we have encoded them. Once again, these models small, very quick. Encoding is usually, with embedding models, the longest operation that is needed. The actual lookup is a fairly straightforward and fast and efficient process. The encoding is usually what takes the most time. Of course, we only have 3 sentences. It's going to go instantly. But there we go. So now we can calculate the similarity of these sentences between them to see what they look like. And we get out this lovely list of numbers, which I'm sure doesn't make a lot of sense unless you've seen this before. So the way to read these sort of similarity charts when you see them is each of these rows correlates to each of our sentences, right? So these numbers are all related to the first sentence. These are all the second one. These are all the third one. And the way that it works from there is for each of these rows, these values correlate to how similar that sentence is to the other ones, and they go in order. So this first row is that first sentence, the weather is lovely today. The first value in that row correlates to the first sentence. The similarity scores, I should have noted, are all out of a percent. Now they are a number version of that percent. So you will see decimal, 1 being 100% the same, 0 being, 0% the same, and everything in the middle there. So of course, when we are looking at the first sentence, the first value in this row is going to be 100% the same because we are just seeing what the similarity is between the first sentence and the first sentence. The next one is once again the first sentence, because like I said, everything in this row is the first sentence compared to the second sentence. So this value here, which is 66.6%, is the weather is lovely today and it's so sunny outside. That is the score between those. And the last one here, which is 10% similar, is once again our first sentence, the weather is lovely today. and he drove to the stadium. Only 10% the same. Now we can see when we look at these sentences that it does kind of make a little bit of sense. Now, whether you think those scores are too high or too low is really based on the model's training, right? If you think that the first and second sentence are more than 66% semantically similar, that's a little bit up to you. That's a little bit up to the domain. That's the stuff we'll talk about, the fine tuning. But we can kind of see, right, when we think about the first sentence and the second sentence, they're both related to the weather. They're both kind of related to outside. They're not ridiculously similar because one said sunny and one doesn't, but they're both related to the weather, are more similar and quite, a bit more similar than the first sentence and the last sentence, which has nothing to do with the weather, right? He drove to the stadium. So that is how you can kind of think about that here. Now let's get a little bit further down into this. The second one is compared to all of the same values. So that we can see 66.6% for the first sentence to the second one. The next one, the second sentence to the second sentence again. And then the last one is the second sentence compared to the third sentence. You're going to see these values all repeat because, eventually you just make your way through the whole matrix of possible combinations. But these two are 14% the same. Now that does make a little bit of sense. Why is this one 4% higher than the first comparison, right? They're both low, right? Both of these are very not similar. Once again, the second sentence is related to weather. The third one is not related to weather, but they are both related to being outside. One specifically says it. One is doing an operation, related to being outside. So that's why when you think about it like that from a similarity perspective of, when you look at these two boxes of text, how similar are they in the way that they're used to explain things? We can see that it is slightly more similar, right? It has more that is related than the one before, which essentially had, nothing. I'm sure, because it is 10%, there's something, in the way that those sentences are commonly used in the English language that makes them somewhat similar. But we can see that that second one and that third one are slightly more the same for that reason. And then the last row, these are all repeat values from before. It's the third compared to the first, and then the third compared to the second, and then the third compared to itself. So that's how to read these similarity scores and how to think about the way that they work and why you get the values that you get when you go through that. So we can see they are, semantically similar, and then they're not the same from there. So we can use this concept of similar sentences to do a very basic version of RAG. This is, like I said, the little tool, the little piece that is used in the middle there to make decisions about what information do we use from our knowledge base to answer a query from, some sort of user input or something like that. So here's a little example here. So install the SBERT model. We have already done that. A couple of other imports we need here. The sentence transformers, we need OpenAI, and we need NumPy. Here's an example knowledge base. It's just a whole bunch of different sentences, different facts, right? Of course, a real knowledge base where you would need RAG is, much larger documents and documents. But we can see we've got a couple different information points here that really matter. We are again going to encode all of this information. We are going to load up that same sentence transformers model. A query is going to come in. Who painted the Mona Lisa? We are then going to look at our knowledge base, find the most relevant information points, grab those, and then answer the question. Now, it's an example. the LLM could probably answer this question without any sort of knowledge base, without any sort of facts, but it gives you an idea of we're able to grab facts, we're able to grab knowledge from a database and use it to answer questions that maybe are a little bit more complex. And we will look at examples that are much more complex as we move forward. We are going to encode the query so that we can do the comparison between everything that's in the knowledge base and what we have as our input. We are going to compute the similarities for those. We are going to grab the top results, the most similar results. We're going to grab the top three. And then we are going to run our system from there. We're going to look at how similar these are, just some print statements so you guys can see what it looks like. And then we're actually going to run the model from here. We've got a simple prompt that just takes in the context, takes in the query, and then says generate an answer. So I'm going to run this. We are going to let it run. And we can see here, query, who painted the Mona Lisa? The top matching knowledge pieces are these three. Right here, we can see one that is incredibly similar. Of course, the Mona Lisa was painted by Leonardo da Vinci. That is, of course, going to be the most similar. 88% is actually a fairly high similarity score. You will sort of see that, just because two sentences are very similar does not mean it's 100. Or even in the 90s. 88 is actually a very high similarity score to be able to have there. And we can see these other two that are just related to France are more similar than the other ones. They aren't, very similar at all. They don't even help us answer the question at 13% and 12%. But just due to the fact that they are related to France, they are somewhat more similar. And we can see we get out an answer here, Leonardo da Vinci. So hopefully that makes sense in the way that we use SBERT to understand the similarity between, two different information points. Sentences, paragraphs, a paragraph in a sentence, different ways that we can do that there, and how this affects RAG, because it is, of course, very important for the actual RAG pipeline from there. Now, the other thing that SBERT can provide us is cross-encoders. Cross-encoders are very similar to an embedding model. They do give us a similarity score as well, but they are much slower because of the way that they compute the comparison between sentences. They are not usually used as the lookup piece in a RAG pipeline to do that initial comparison. They are usually used for what are called re-rankers. So in very difficult domains where, when you get the results in terms of what is similar to a query from a knowledge base, and let's just say your system's very bad at doing that, just because the domain is hard. The language that is used in the knowledge base is very different than what the general model is trained on. Remember, SBERT and all of these other embedding models are trained on a general corpus of text, Wikipedia, internet stuff, books. So if you have a specific domain or a specific use case where that language is very granular, it's very specific, say legal, medical, something like that, it's not going to perform as good out of the box because the way that language operates in that specific space is usually very different than the general text, right? When you think about the space of all of the English language, any text that is legal related is going to look somewhat similar when you compare it to everything. Remember, our model is trained on a general corpus of information, so anything in one little niche is just going to look more similar, which will cause issues in the RAG pipeline if all of your text looks, either very similar or very not similar. Cross-encoders or re-rankers, they allow you to sort of almost double check and literally re-rank the results of what's most similar to a query. The reason you use this in sort of a smaller re-ranking workflow is that way you don't have to do all of this similarity score computing on everything. You can use the embedding model to, essentially get the top 10 or 20 most similar results to a query, and then use the re-ranker to get, say, the top 3 results from there. That way the re-ranker only has to run on 20 results instead of the embedding model running on, maybe thousands of results in a knowledge base. So they're very straightforward to use. It's essentially the same process, just slower. So we're going to load this model up. Um, I will tell you that we use re-rankers in our RAG pipelines. Most of the domains where this stuff is needed at this point are more complex. So we do fine-tune the embedding models, which we will talk about, of course, in the future, as well as use re-rankers here on some of the larger corpus that we have. So we download it. We can see once again we have a query. We have our corpus of information, a bunch of different sentences, and then we are going to rank them in order from most similar to least similar. So I ran it. It does finish pretty quick on a small example like this, but you can imagine production pipeline, everything like that. It is a little bit different. This is actually the Roberta base is not the largest of re-ranking models. And we can see here that compared to the query, a man is eating pasta, a man is eating food is by far the most similar. The sentence almost reads word for word, other than we have two sort of different levels of domain, if that makes sense. One is specific to a food item, one is general about food. And then once again, it does pretty quickly move down from there, but we can see a man is eating a piece of bread is not as similar as before. The sentence is longer. It's not as directly the same in terms of the keywords as the one before, but it is infinitely more similar than the rest of this, where these 3 are all related to eating food. And of course, nothing else from there is related to eating food. So you can see the large difference in information when we go from 34% and essentially drop off a cliff from there. So, pretty straightforward there in terms of what we use it for. Like I said, I don't usually recommend using re-rankers on everything, especially if your domain is very large. Stuff like this, or re-ranking or smaller corpus of text, it's fine. It's just another option. There you can fine-tune re-rankers as well, although we usually don't. But it is another option that is offered by the SBERT system. From there, we can also take a look at the sparse encoders. This is very much the same as what we see before. It is a little bit more high level. It is focused on sort of larger scale retrieval than the examples we've given so far. It works identical to what we've seen before, where we load up the embedding model. We have our sentences to encode. We encode them, and we get our similarity score from there. So, pretty straightforward. Nothing really changes other than the fact that it is just used in a little bit of a different architecture than something that is out of the box. Usually more of an advanced use case than somebody just getting started with RAG and just kind of, wanting to play around with some use cases from there. So that is it. This is where we will start, is with SBERT. I will probably go through the fine-tuning video next. And then from there, go into more of a general what is RAG, and then do some parts from there. But did want to start with each of the individual pieces of the pipeline so you understand how they work, outside of that domain, and can make decisions on what to use, based on actually understanding the tools, instead of thinking that RAG pipelines always have to look the same. So I hope you enjoyed. I hope you gained some knowledge today about the way this stuff works, and I will see you in the next one.